This is exercise 2 on page 76 of your workbook. Okay, and hopefully you've made an attempt at this exercise before you take a look at this video. So we'll run through this the same way that we did with the preliminary example. It's sort of similar in spirit, but the geometry is a little bit more complicated. Okay, so let's read the problem together. So we've got a farmer again with a certain amount of fencing, 100 total meters in this case. And this time we want to fence a field that has a rectangular area, but then add another line of fencing to divide the field in half. You can kind of see that in the picture over here to the right. Okay, so we can maybe approach this the same way we did the previous one by giving these lengths and widths some names. Okay, so how about if we call the length of the top of our big rectangle, the entire field, x, okay, and then the height of the field, y. Okay, so we've got a y here, and a y here, and then another x at the bottom. Okay, so we can kind of see all of the places that we've got that we're going to lay down fence. Okay, and we'll start the same way that we did with the preliminary example by asking, what are we given in the problem? Okay, well, again, it's the amount of fencing that they tell us. All right, so we need to look at the picture and see how many different lines of fencing we have. So notice that there are 2 lines of fencing at the top and the bottom of the field. That's x and x again. So there's a total length of 2x of fencing across the top and the bottom. And then we've got 3 vertical lines of fencing here, here, and here. Okay, and so that's another 3y worth of fence. And so all of those lengths have to add up to the total amount of fencing that we have, which in this case is 100 meters. Okay, so that's what we know. And what are we trying to find? Okay, well, we'd just like to know, out of all of the different shapes that we could make this field, the variations on x and y that we could use, which would give us the biggest area? Okay, so x and y that maximize the total area. Okay, we'll call the area A. So as before, if we want to find a maximum area, we need a formula for the area. Okay, so we're dealing with a rectangle again. So the area of the entire field, and remember, that's the area of the big rectangle on the outside, that's still going to be x times y, because we called x the entire length across the top. Okay, and we have the same issue that we did in the preliminary example, and that is we can't find critical points of this area function unless we just have a function of one variable. So we need to eliminate one of the variables. We're going to do that in the same way that we did before, by going back to this given information and just trying to solve for one of the variables. Okay, so let's see if we can sneak that into the space here. If 2x plus 3y is 100, let's take that equation and just solve it for y. Okay, so we can subtract 2x from both sides. Okay, and then go one more step, divide through by 3, and we're going to get 100 minus 2x over 3. Okay, meaning that everywhere that we see a y, we can put 100 minus 2x over 3. Okay, so we'll go back to our equation and we'll do that. Okay, well, to find critical points, we now need to take the derivative of this area function, but you might notice that would be a little difficult to do given the form that our equation is in. X times the fraction, 100 minus 2x over 3, that would be a pretty complicated derivative. There's a product in there, there's a quotient in there. And so a question we might ask ourselves is, can we simplify our function? Okay, just to make the taking of the derivative easier. All right, well, we can if we do a little algebra here. Okay, so let's first take the x that's in the front and just multiply it through the numerator. Okay, so that our function looks like that. And then another way of rewriting this is to think of that over 3 that's in the front as a fraction, 1/3, that gets multiplied by the original numerator. Okay, 1/3 times the quantity 100x minus 2x squared, that's equivalent to the fraction that we started with. And writing it that way is going to make the derivative easier to take. Okay, so let's do that. We're ready to find our critical points here, so we're going to take the derivative of our function, and I'm going to use this form of the function. So the 1/3 is a constant that's out front. We can just pull it out, and then multiply that 1/3 times the derivative of 100x minus 2x squared. Okay, so derivative of 100x is just 100, and derivative of 2x squared is 4x. Okay, we'll take that and we'll set it equal to 0. Okay, so this becomes an algebra problem, and we might start by just multiplying both sides by 3. Okay, that's a way of getting rid of that denominator over here on the left. Okay, and over on the right, 0 times 3 is still 0. Okay, so that's going to get us to 100 minus 4x equals 0. Okay, and that's an equation I think we can solve without too much trouble. All right, so we'll add 4x to both sides, and we'll divide both sides by 4. Okay, but 100 minus 4 is just 25, so we have one critical point that looks like x equals 25. Okay, and we're hoping that that's the number that's going to yield the maximum area here. Just to check that, we can do a sign chart. Okay, and I'm not going to go through the entire calculation of the sign chart here, but just kind of remind you of what the steps are that would be involved there. Okay, so we'd take our one critical point. Okay, you would choose a couple of test values, one number that's a little less than 25, one that's a little bigger than 25. Plug both of those into the derivative, and I'll ask you to maybe confirm on your own that if you do that, you're going to get a plus and a minus. Okay, and you can see from that that we do indeed have a maximum area at 25. Okay, so we'll just make a remark here. The chart to the right indicates a maximum value of a at x equals 25. Okay, so we know then that this 25 that we calculated above, that's the number that we want. Okay, so we're ready to state our answers here. And if you look back at the statement of the problem, they asked us for two things in this case. They wanted the dimensions of the field, the value of x and y, that give us the maximum area, and they also wanted the maximum area. So let's do those one at a time. We have already calculated and confirmed that x is 25. That's a length, and it's in meters in this case. We need to figure out what y is. Okay, and so there, we need to scroll up and see if we can find the formula for y that we had. Okay, I'm going to use this one. Okay, we solved for y and discovered that it's 100 minus 2x over 3. So we'll take 100 minus 2 times x, which we see from above as 25, over 3. Okay, and you can confirm my arithmetic here. That turns out to be 16.7. Okay, so far what we know is that to get the biggest possible area, we want to make the width of our field 25 meters and the height of it 16.7 meters. So there are two of our answers. And what's missing is the maximum area here. Okay. So the area we can get by taking the formula for the area and just plugging in x equals 25. All right, so here we need to scroll up again and see what formulas for area do we have available. Well, there are actually a few of them. Okay, if you look at this line, we wrote the area in several different ways. So we could actually use any of the formulas on this line. I'm going to use the very last one here because it just involves x. So we'll take 25 and plug it into there. Okay, and what we get should give us the maximum area. Okay, and again, you can substitute these numbers in yourself and just confirm that that all works out to 416.7 if we round off. What would the units on this number be? Okay, well in this case, since our lengths are in meters, we should be getting area in meters squared. Okay, and so to summarize, we are looking at our three answers. The dimensions of the field, that's the x and the y, and then the area of the field is the last calculation. And we are done.